So I will just jump right into the topic here. So for the past 15 years, me and my research team have focused on using AI and multi-agent systems research for social impact, focusing on topics of public health, conservation, and public safety and security. With the question, how to optimize our limited intervention resources, let me just jump right into one of the lessons we've learned, that achieving social impact and AI innovation go hand in hand. With respect to public health, the challenge is we have large populations to serve and limited number of public health resources. Concrete example is work we have done with youth experiencing homelessness in Los Angeles. Harnessing the social networks of these youth, we are able to show that our social network algorithms are far more effective in spreading HIV information and reducing HIV risk behaviors compared to traditional approaches. This work required innovation in the area of social network algorithms and bandit algorithms. With respect to conservation, we have large conservation areas to protect, a limited number of ranger resources. Concrete example is work we've done in Uganda and Cambodia, where harnessing past poaching data, we are able to predict where poachers set traps or snares, and for the past several years have been able to remove thousands of these snares. This work required innovation in the area of green security games, which combines machine learning and game theory. With respect to public safety and security, we've contributed a new model called Stackelberg Security Games and contributed new algorithms based on these models that have been used by security agencies in the United States, such as the Federal Air Marshal Service, the US Coast Guard, and others. So these areas may seem like they are quite different from each other, but what ties them together is that underlying all of it is multi-agent systems research, which is the common area of research that cuts across these areas. A second lesson is all of this work requires partnerships with communities and nonprofits. I've shown here logos of some of the nonprofits we have worked with. Our ultimate goal is to empower these nonprofits to directly use AI tools and avoid us being gatekeepers to AI technology for social impact. So today, given our limited time, I'm going to focus on two projects. One done at Google Research India on maternal and child care using this technique of restless bandage, and the second done at Harvard on HIV prevention using social network algorithms. So with respect to maternal and child care, we know the situation in India is difficult. A woman dies in childbirth every 15 minutes. 4 out of 10 children are too thin or short. We are very fortunate to be working with a nonprofit called Arman, which works with 25 million women in India. One of their programs is called Mitra. It's a weekly 2-minute automated message given to mothers when they're expecting. They enroll in the Mitra program and they start receiving these messages. The messages may be of the form, you are 3 months into your pregnancy, you should use this health supplement, or your baby is 3 months old, enroll them in this government program. So the messages continue all the while from the time the mother enrolls when she's expecting to the baby being 1 year old. In randomized control trials, Arman has shown that this Mitra program leads to significant benefits to mothers and babies in terms of their health. 2.2 million women have enrolled in Mitra. So where do we come in as AI researchers? Unfortunately, a significant fraction of these women who enroll may ultimately become low listeners or drop out of the program. Arman has a call center from where they can make a limited number of service calls to these beneficiaries, to these women, to retain them in the program, to have them listen to these health messages, which are clearly very important. And the question is, which mother should they call? So supposing we have N number of beneficiaries, which is large here, like 200,000, and we have to choose 4,000 per week to give service calls to, so that we maximize the number of health messages that the mothers have listened to. I'll give a simple example to illustrate. Supposing we have a health worker, in this case, I'm only showing 5 mothers in her care. 4 of them shown in red have not listened to this Mitra message last week. 1 of them shown in green has. She can only call 2 beneficiaries this week to remind them to listen to these messages. Which 2 should she call? Supposing she calls the first two, this turns out to be a good choice because they were red, they turned to green. That is, they started listening to the Mitra messages this week. A third mother also turned green. Now she has to decide, the remaining two are still red this week. So next week when she decides, she has to decide which two mothers to call. Supposing she decides these two mothers which are in red, this turns out to be a bad choice because these two mothers remain red, but the other two which were green earlier have also turned to red. So the point here is that a service call may not change a beneficiary state from non-listening to listening. However, beneficiaries may change state on their own from red to green or green to red. And yet, we have to prioritize 4,000 beneficiaries per week from the 200,000 that are enrolled in the program. We appeal to restless bandits to solve this problem where we can choose K out of N arms per week. For those who may not be familiar, restless bandit model, each mother is modeled as a Markov decision problem. So a mother can be in a bad state, she didn't listen to a message, a Mitra message, or a good state, she did listen to a message. There's transitions between these states. So if we do not give a service call, the mother has a higher probability, 0.8, to remain in a bad state. If we do give a service call, the probability of going from a bad state to good state increases here to 0.8. So in reality, we have each mother modeled as a Markov decision problem. So we have 200,000 such MDPs, and we have to now decide which K arms to pull, which mothers to give service calls to. Now, if you imagine solving this problem of choosing 4,000 out of 200,000, 200,000 choose 4,000, that's a massive, massive number. These are very difficult problems to solve. So we solve this problem by computing what is known as a Whittle index. Essentially, it is computing the benefit of intervention of each mother separately and then choosing top K of these mothers. We use an algorithm that we defined earlier in Chen et al. Amos 2016. And what it's trying to do informally is to figure out how much subsidy to offer to each arm so that the benefit of not calling is equal to the benefit of calling. And when that happens, that's essentially the amount of subsidy that's offered is the Whittle index. For those who may not be familiar with this whole approach, just remember that there is this technique of Whittle index to determine which K mothers to call. However, this Whittle index requires that we know the transition probabilities in advance. We, of course, do not know the behaviors of the mothers in advance. So we learn it from past data. We have past beneficiary data, which shows us the features of each mother, that is age, income, education level, number of children, etc. And engagement sequence, that is she was in a non-listening stage. When we didn't call, she remained in a non-listening stage, or she was in a non-listening stage. When we called, she moved into a listening stage, etc. So based on this past data, we learn a model. We first cluster these mothers into different clusters and then learn a mapping from features to clusters. So now we know for a certain mothers of certain age, income level, education level, what are their transition probabilities of moving from bad state to good state. So when we get a new batch of beneficiaries from their features, from age, income, etc., we can predict which cluster they belong to. That is, we know their transition probabilities, from where we can compute their Whittle indices and then determine which top K mothers to call. So clustering compensates for lack of data that we have and also speeds up our Whittle index computation because we are not computing a Whittle index for each of the 200,000 mothers, but only for these clusters of mothers at a time. We conducted a study of 23,000 beneficiaries. This work is actually recently accepted at AAAI 2022. As far as we know, this is the first large-scale application of restless bandits for public health. And so here we created 3 groups. One was a restless bandit group, one was a round-robin group, and one was a current standard of care group. So with 7,667 mothers in each group. In each group, we pulled 225 arms per week for 7 weeks. That is, we called 225 mothers per week for 7 weeks. Which 225 out of the 700,667 in the RMAP case, in the restless bandit case, essentially we use the Whittle indices to determine the top 225. So top 225 Whittle indices. In the round robin case, basically we were calling mothers sequentially. First 225, then the next 225, then the next 225. This is to show, to take an approach where the calling was not optimized. Current standard of care group gives no calls to mothers. This is the current standard of care. And now we want to know how many more M-Mitra health messages were listened to over the current standard of care group, in the RMAP group, in the round robin group. And what we find is here, on the x-axis are different weeks. On the y-axis, cumulatively, how many more messages were listened to over the current standard of care group by the RMAP group and by the round robin group. That is, we find that the blue line, which is shown by the restless bandit group, the 7,667 mothers who are in the restless bandit group, we find that they listen to far more messages compared to the round robin group. This result turns out to be statistically significant. So restless bandit versus current standard of care, the difference due to the blue is statistically significant. Round robin versus current standard of care is not significant. The point here being optimizing which mothers to call is very important in order to get more mothers to listen to these calls. And just calling mothers sequentially, etc., doesn't make any difference at all. It's not statistically significant improvement over not calling the mothers at all. So this is a technique. Now we've launched a new 100,000 beneficiary study in collaboration again with Arman. And the goal here is to really transition the software over to Arman soon so that they can start using it. More mothers can start listening to these messages. The founder of Arman, Dr. Aparna Hegde, there's a video on YouTube. I hope you will watch it. And I praise the video because of the team that created the video is very talented. This is AI for Social Good in partnership with Arman, a Google video. And so she's saying here in the video that we are able to reach out to more and more women each week and get them back into the fold and save lives because of AI. There's also a very touching image of a mother who talks about taking care of a baby, that I follow all the advice from M-Mitra and take good care of my baby. There are many other applications of these restless bandits. Tuberculosis is one. Tuberculosis causes 500,000 deaths per year in India. 3 million people are infected every year. And patients have to take these TB treatment pills for 6 months. And the question again is that, for me, even taking 1 week course on antibiotics is difficult. For patients who have to take this for 6 months is extremely difficult. And so they drop off of treatment, which is bad for them because of drug-resistant bacteria also that this leads to. So health workers again have to ensure that the patients actually take their medicine every day. Again, we face the same problem. There's a health worker with a lot of TB patients under her care, and she has to decide which patient she could call because she can't call all of them every day. So supposing she calls the first 3, now she knows that 2 of them took their medicine last night, 1 of them didn't. And she encourages them to take their medicine and then decides which 3 patients to call tomorrow, and so on and so forth. This problem is similar to the problem I showed with Arman, except the state of the patients is not known in advance. So this is a problem of restless bandits with partial observability. We have done a simulation study that was published in NeurIPS 2020 and shown that our algorithm shown in blue is much faster than the state of the art while losing very little in terms of solution quality. There are lots of interesting challenges here, but in the interest of time, I'm going to move on to the next topic, which is social networks for HIV prevention work that we did with my group at Harvard. And so this is work for youth experiencing homelessness in Los Angeles. I was in Los Angeles at the time, and outside our university there was a camp of homeless people. And so that's what motivated this research. 6,000 youth sleep on the streets of Los Angeles every night. The rates of HIV in this population are 10 times the rates of the normal house population. So homeless shelters or drop-in centers can't reach all 6,000 youth, but they try to recruit peer leaders, educate them about HIV prevention, expect them to talk to their friends and their friends to talk to their friends, and in this way, information to spread about having safe sex, not sharing needles, etc. This is all face-to-face interaction. This is not happening over Facebook, for example. So if you think about it in terms of a social network here, each number here is a homeless youth. Each red line is a friendship edge between one homeless youth to another. And we have to select from these, let's say, 3 youth here, C, F, and H shown here, who are the key influencers we have selected so as to maximize the expected number of influencers, maximize the number of youth who were reached. And this is a picture from our colleague in social work educating the youth that were selected. So here information is supposed to spread via this independent cascade model. So you educate the youth C about HIV prevention, then with the probability of 0.4, their friend D will get informed about HIV prevention, and when D gets informed, D's friend E gets informed about HIV prevention with a probability of 0.4 and so forth. So information spreads by cascading through the network. So why are there research challenges here? If we look at standard research algorithms that have been published in the literature, what we find is they assume that a lot of information is known. In reality, this propagation probability 0.4 that I mentioned is not known. We have to handle the fact that peer leaders who we invite may be no-shows. In fact, the social network itself is not known in advance, and we can query a small fraction of the network to uncover it. Again, in the interest of time, I'm not going to be able to go through how we addressed each of these problems, but I'll sketch out some ways we solve the first challenge just to give you a flavor of the kind of approaches that we've taken. So as what I said is that previous algorithms have assumed that if there's a youth C who's informed about HIV prevention, that their adjacent youth D will be informed with a probability of 0.4 that is known. In reality, we may not know this probability. We may sample it from some distribution. We may not know the mean of this distribution, so we assume that the mean lies within some interval. So now we have this problem of robust influence maximization, how to spread influence when we don't even know the transition probability. We do this by casting it as a game against nature. So we, in our algorithm, are trying to choose the top peer leaders to spread influence, the top influencers. Nature is trying to choose parameter settings to cause our algorithm to perform as worse as possible. So we are trying to maximize influence, but nature is trying to minimize influence. And our reward here is the outcome of our choice of influencers to the optimal possible had we known nature's parameter choices in advance. There's some details here of mixed strategies and pure strategies. For those interested, they can look at our AMAS 2017 paper. But let me sketch for you how we solve this game. So the influencers' choices are shown along the rows. If there are 400 youth and we want to choose 40 of them as influencers, that's 400 choose 40. That's a massive number of policies for the influencer. Nature is trying to choose parameter settings to cause our algorithm to perform as worse as possible as to what is the probability of influence. Nature is choosing these probabilities from a continuous interval. Nature also has a large number of columns here from where it can choose. So the game is so massive, trying to solve it is difficult. We can't even represent it in memory. So the way we solve it is by using what is called a double oracle approach. We initiate the game with small number of strategies, both on the influencer side and nature side, maybe 2 or 3 each. And then there is this double oracle approach where the influencer's oracle will add iteratively the next best policy. Nature's oracle will add the next best set of parameters. And we iterate in this fashion until convergence, and we can show that we converge with approximation guarantees. Hopefully that gives you a sketch of how we can solve these games and obtain robust policies for choosing the right influencers. Okay, so we solved the problem of network sampling, robust policy generation, multi-step policy generation. I haven't covered all these topics, but We created a system, it's called Change. And now we did a study with 750 youth. This was conducted in collaboration of Professor Eric Rice of social work. So we had 3 arms here: Change, which is our algorithm; Degree Centrality, which is the traditional approach, bring in the most popular youth because they would be better influencers. That's the idea. So homeless shelters will bring in popular youth. This is the Degree Centrality approach. And the control group where there is no influence spread at all. And we want to know at the end of 1 month and at the end of 3 months, what was the change in behavior? So was there an actual reduction in HIV risk behaviors? And who caused it more, due to change or degree centrality? So we did this study with 3 homeless shelters in Los Angeles: My Friend's Place, Los Angeles LGBT Center, and Safe Place for Youth. This is the first large-scale application of influence maximization for public health. So there were 3 groups, as I said. In each group, we selected influencers. In the change group, using the change algorithm; in degree centrality, the most popular youth; in the control group, there were no influencers chosen. And at the end of 1 month, we looked at what was the change in behavior. This is a HIV risk behavior, reduction in condomless anal sex. At the end of 1 month, change caused highest reduction in this HIV risk behavior. With degree centrality and control, there was no difference, no reduction. At the end of 3 months, degree centrality begins to catch up, but still it's lower than change. The point here is that change causes this reduction in HIV risk behavior faster. And that's important because it is a HIV risk behavior, and also because this is a community where youth come and go, and therefore having this reduction happen faster is important. We saw a similar reduction in condomless vaginal sex, which is another HIV risk behavior. So our AAAI paper gives statistical significance results if people are interested. Our collaborators were thrilled with this result.
Beautiful way to kind of like marry this tech world with this social service world, like, and how we can kind of go deeper and impact young people and elevate them.
So I'm going to just go through a couple of the lessons that we've learned. Achieving social impact and AI innovation go hand in hand. We are really trying to empower. We should, in AI for social impact, empower nonprofits to use AI tools. We have to look at the entire data to deployment pipeline. This is not just about improving algorithms in the lab. It's important to integrate these AI innovations in the normal workflow of an NGO. It's important to step out of the lab and into the field. And embrace interdisciplinary research, whether with social workers, with conservation scientists. Finally, lack of data in this area is the norm, a feature and part of the project strategy. So I'll end here. Thank you all for listening, and I'm open to taking questions. Thank you. And that's my Twitter handle in case you wanted to follow up on some of our papers. Thank you very much.
Thank you, Professor Milind. First of all, I'm going to take the stage and say I'm a big fan of your research, which of course, the academic research on one side, and the way that it translates onto real world problems. For instance, the way of, the problem of handling poachers in different places in Africa, and the project that you've been doing with Arman, and currently this one to help the youth in the rehabilitation program. So I'll start with, I'll break the ice with some of the questions, and then we can go over taking some of the audience questions.
Yes, definitely.
My question largely was a tangent on the project that you've been doing with Arman. So there's this baseline, let's say, transition matrix for all these women that are enrolled in this Arman program for maternity care. And the question is that I understand for TB treatment, where people might not like to take drugs after a few weeks, maybe because of the way they feel, or maybe because of the money that goes into buying these. But one would imagine that a woman is, really concerned during, this time when she's, bearing a child. So why would women drop out? And if you got some insights from what kind of women, what demographics they have, the ones that do end up dropping out, and whether some kind of policies and interventions can change the baseline transition matrix. So I know that's a lot of stuff to unpack, but I'll leave you with that.
What a wonderful question. Thank you so much. And I wish, Dr. Aparna Hegde, who's the founder of Arman, were here, because she may be able to provide more domain level insights that I, as a computer scientist, may not be able to offer. But we do see that mothers begin to drop out. They just stop listening. And what socioeconomic factors, etc., go into why that happens, I'm not entirely clear. One of the things that happens in the service calls is that the mothers who get called will point out, because these are places where the phone may belong to the husband, and the woman is using that phone in the evenings only, when the husband is home, in order to listen to a message. So they may point out that, they are not getting the call at the right time. The call is going to the husband during work time. So change the timing of the call. Or there may be other such causes as to why women are dropping out. So sometimes they're not dropping out intentionally. It's just the situation that they are in, they're just not able to listen to the call. And so we have to make adjustments, to the time of the call, or there may be other such changes that are needed. But it's an excellent question, and I should definitely try and investigate more with Arman as to what motivates women to start dropping out of the program. But it's worth investigating. Thank you for that question.
Right. Thank you, Milind, for taking that up. I'm going to check briefly for the questions that have come up. Right. So one of the questions that's come from the audience is that the accuracy of the interventions of the kind that you've been doing with Arman relies heavily on the quality of the data. And in India, getting quality data good quality data is very challenging. So what are some of the concerns and challenges around that you've come across while doing this project?
Again, an excellent question. And as I pointed out earlier, in this area of AI for social impact, we just have to accept that data will be low quality, it will be insufficient. And so we have to just accept that and work that into our project strategy. So one of the points here is that we are not at this point trying to aim for perfections. In the first state, we are just trying to beat the current state of the art. And so we have certainly shown that compared to the current standard of care, which is no service calls going out, or essentially randomly giving service calls, we are doing significantly better than that. So even with the quality of data that we have, we are able to improve upon the state of the art. So all is not lost. So there is hope. Secondly, we are using techniques like clustering of women, so that even though we have limited data on an individual woman, because of this clustering, there is collection of data that comes together, and therefore there is more robust sort of transition probabilities that we are building up. I didn't get into it, but there are clearly very interesting research challenges, such as we have to account for the fact that these transition probabilities are not 100% accurate. So rather than saying that they are 100% accurate, can we build more robust algorithms that are tolerant to error in these transition matrices? This is a new area. This has not been addressed before in the area of restless bandage, and it's something that we are actively exploring. So there are lots of very interesting research challenges that come about due to the lack of data, whereas trying to get more accurate quality data is one way to solve it. Another way is to say that is the way the data is, and can we then compensate for that using algorithmic methods?
Great. Fantastic response. Thank you, Professor Milind. Another question that I find really interesting is with regards to the second project that you were discussing, can influence maximization make traditional digital marketing tools obsolete? So, this fact of being able to choose the right people to disseminate, can it really bring down the load on, traditional manners or maybe this style is already incorporated in the traditional mechanisms of digital marketing? I'll leave it upon you to answer that.
So this problem of influence maximization comes from marketing as the original problem. So there is 20 years of work on influence maximization in the AI literature. Before we started looking at it as an approach to addressing the challenge of HIV prevention among youth experiencing homelessness. One huge difference, though, is that when we talk about this digital marketing and so forth, at least in the papers, the assumption has been that the entire social network is known in detail. The influence propagation probabilities are mostly known. So a lot of data is assumed to be available in order to choose wisely which influencers. In our case, the main difference is you go to a homeless shelter. We started with an algorithm, and we can do influence maximization in social networks. If we go to a homeless shelter and say, you give us your social network of your youth and we will tell you who are the key influencers by running our algorithm. And they say, well, we don't have one. There's no social network. You have to do a survey. Now, who's going to sit there and do a survey? I mean, you could, but this is really very difficult to sit there and do a survey of all of the youth, who's friends with whom. Instead, the challenge then that we took upon ourselves is, can we sample a small fraction of these youth? So you get a small sampling of the social network, maybe 10% of the people only. And from there decide which of the youth are the key influencers. So that's the problem we solved. Again, going back to the earlier question, we have to accept the fact there is no data. We can't complain that there's no data, so we can't solve the problem. Can we compensate for it by coming up with an innovation in the algorithmic space, which is what we did. And so with respect to the question, the key difference between this marketing literature and what we are doing is the lack of data. So that's the key innovation, that's the key difference. And so there'll be many such applications where we are working in communities that are marginalized, underprivileged, where we don't have data, and where these kinds of techniques can be used for influence maximization.
Thank you, Milind. There's Professor Gopinath from the faculty who'd like to directly ask you one question. Please, Professor, go on.
Yeah, hello. Can you hear me, please?
Yes, absolutely. Yeah. Yes.
I'm going back to that question about whom to call. With respect to that maternal health problem or issue, isn't it the case that there is some minor amounts of information available to you? For example, whether it is the first-time pregnancy or the youth of the person, can't it discriminate because the first-time pregnancy or the youth probably might be much more anxious about things, about how things are going to work out. They'll have a different profile than experienced mothers, let us say. Okay?
Yes.
So I think that could, I'm just saying that there are some additional factors in your hands, and similarly, I think for TB also. Okay? So would those things not, let's say, help you to do a more, quote, targeted way of doing things?
That's a great question. So we do have that information about number of children from the mothers that have given that to us, given that to Arman. And so we use that information in order to learn the transition probabilities. Perhaps we could do an even better job, but basically it's mapping these features: age, income, like you said, age, income, number of children, education level, using that to map those features into the transition probabilities of those mothers. Basically, transition probabilities here is a shorthand for behavior of those mothers. So you're exactly right that mothers who have a certain profile may behave in a certain way. And that is what we are learning through our machine learning clustering algorithm. And then we use that when new mothers come in and we do not know their transition probabilities, their behavior, we say this mother has a certain set of features, and therefore she's going to behave in this particular way, which we have learned in the past. So complete agreement with you.
This is basically establishing the prior in some sense.
Right. Basically, essentially we're just learning a mapping using past data. So that's exactly what's going on.